Hello, everyone. My name is Dr. Deepen. We are joining once again for the YouTube Wagner on Ethics and Leadership series. From the last discussion on the personality of mathematics about 2 years ago, we received a great feedback, and some of you requested that we do another session on the math of personality of mathematics with little more details. So here we are. Today we have Dr. Wagner again. Dr. Wagner has served as the full-time professor of philosophy and logic with the College of Human Sciences and Humanities at the University of Houston Clear Lake. He also is a professor for STEM education with the College of Education at the University of Houston Clear Lake. He served as a former vice president of Association of Philosophers in Education. He also was former executive secretary of the Philosophy of Education Society. A number of years ago, he worked with Professor Patrick Suppes on the computer assisted logic program for undergraduate students at the Stanford University. And we can go on and on and on and on about who Dr. Wagner is. Um, we will go ahead and ask him about the book Personality of Mathematics and get you guys some insights into the the book itself and the motivation and the purpose behind it. Good afternoon, Dr. Wagner. How are you today, sir?
I'm just fine. How are you?
Doing well, thank you. Today's first question. The book is full of technical episodes in the development of mathematics, but it also has much practical learning recommendations for making math more accessible to all. Which do you start with?
Well, when we think of mathematics, all too often those who aren't really involved in mathematics in a deep way, they think of it as laborious, tedious, threatening, and it's none of those things. One of the things that the book that we're talking about, when we talk about the personality of mathematics, is that we're taking a look at the intellectual experience of math, both for those who succeed in it and as well as the architecture of the discipline itself. Every discipline has its own sort of architecture. People who love history, there's an architecture to history, and there's a reason why they develop a love for that. People who become interested in novels and so on, they have a certain sort of personality that leads them to want to study deeply in the creation of fictional literature, which is beyond that of those who might pick up a book, a novel, just to read for fun. And the same is true in mathematics. To give you just one example, one of my favorite ones, because I think the fellow is still living. A little bit of background about him. His name is Grigori Perelman. He lives in New York City. And to go back about 100 years, probably the most famous mathematician of the time, around 1890 to 1900, David Hilbert had listed 10 problems, 10 mathematical problems that were said to be the most important mathematical problems to be solved at the time. And he was able to get a bank to support the solution to any one of the problems. You get $1 million. So 10 million bucks are sitting there for people that can solve these 10 problems. Also, there are two prizes that go to top mathematicians that are the equivalent of a Nobel Prize in sciences. And a little aside there, a lot of people don't know there is no Nobel Prize in mathematics. And there's been rumors forever about why is it that Alfred Nobel never allowed a Nobel Prize to be offered under his name. And I won't go into the rumors, but it's about personal sorts of things. Even if someone were to offer $1 million that doesn't come out of Nobel's foundation, but like the Nobel Peace Prize, that is, and the Nobel Prize in Economics, those are both funded from outside what the Nobel Prize in Economics is funded outside of the Nobel Foundation. That's the only one of the Nobels that's founded that way. But it uses the Nobel name. So Nobel was willing to have another $1 million put up or more for somebody that wins a prize in a science, but the foundation, the will says no one in mathematics can ever get a Nobel Prize in mathematics. There'll never be a Nobel Prize in mathematics, or else the whole fortune goes back to the descendants of the Nobel family. Why is that? Well, listeners can look that up and see some of the rumors themselves. But I want to return to Grigory Perelman. Grigory Perelman is a mathematician, brilliant mathematician in New York. And he lives in a small apartment. And he solved one of David Hilbert's 10 problems. But he refused $1 million. How many people do you know that refuse $1 million? But he refused $1 million. And we'll find out why in just a moment, because this will tell you something about the nature of math and the nature of its superstars. He also was the two prizes that are given in mathematics outside of the Nobel Foundation, because it gives none, but it's either the Fields Prize or the Abel Prize. And both the Fields Prize and the Abel Prize, very sought after by mathematicians, come with a large amount of money close to that of a Nobel. A lot of money is involved. Well, he was nominated as the Fields Medal winner. One could go on any kind of an encyclopedia that lists the winners to the Fields Prize, and you'll see everyone who was named a winner is there, and they all accepted a prize, except for Grigory Perelman. He was named a winner. The money was there for him, and he refused the prize because he didn't think he deserved the money. Why is that? And Perelman said, because I'm not like a scientist. I mean, scientists, they do things like they invent things and so on. They invent new concepts, intellectual tools, and so on. He said, I'm a mathematician. I just find what's already been there all along. And so he turned down both of those prizes.
Wow.
And he does most of his work just on his own. Every now and then, because he's this incredibly famous mathematician. New York University, which has a superb department of mathematics, they may have him teach a course, but he doesn't want to teach regularly. Columbia University has had him teach a course, so he'll occasionally teach a course. But other than that, he just wants to do mathematics. Now that tells you something about that personality that you don't hear about in hardly any other discipline I can even imagine. Another fellow who I won't go into with quite as much depth, but his name was Paul Erdos. And he was well known in the mathematical community for traveling around the world to visit great mathematicians he had met at conferences over time and so on. And so he would come for a visit and he would stay for, maybe as long as a few weeks or a month and just work on mathematics with them. And then when that was all done, he would leave. He wasn't there for social purposes. He would leave and he would go somewhere else to another mathematician's house. And they knew he was coming. And he would work mathematics with him. And he spent most of his life, as it were, on the road doing interesting mathematics, chasing his bride, the new secrets of mathematics. So they're an interesting group of people, especially those working in the areas of pure mathematics. So when we talk about, mathematics, we're talking about an area of human intellect that is extraordinarily unique and alluring. I'll tell you one other one, just as an aside. Moscow, back in the 19th century, had been a center of mathematics. Moscow, the University of Göttingen over in Germany, those had been superstar places for mathematics in the 19th century. There were a group of, one was even a priest, an Orthodox priest. There were a group of mathematicians that were worried about they might say the wrong thing and the czar would get upset. And so they met in secret to talk about things that were almost mystical in mathematics, such as ideas of infinity and so on. And they were called the ghost whisperers of mathematics. And it was a little group of people, and one was even an Orthodox priest. That shouldn't surprise anyone who's given much thought to infinity, because you start talking about infinity and before you know it, um, you you're almost drawn into theological speculation. Oh, and I can't let this one go either before we go ahead, and I'll come back to him later. You get this one, I know you know, it's Ramanujan from India.
Yeah.
Uh, Ramanujan swore that he would have these dreams at night, and Vishnu would come to him. You know, Vishnu is the top god, right? And Vishnu would come to him and give him the theorems. And he would wake up in the morning, he'd have the theorem, he'd write it down, and he sent it to two of the most famous mathematicians at the time, Littlewood and Hardy, T.H. Hardy up at Cambridge. And Hardy recognized that some of the symbols that Ramanujan was using, he made up himself, but they made sense. And so Hardy knew that here's a genius. So they invited him up to Cambridge, and they kind of hid him from other people in the world, because it was like having this wealth that just kind of walked in that could give you all sorts of interesting ideas. Because while he came up with the theorems, he never thought it was part of his responsibility to come up with the proof of the theorem. But once they saw the theorem, Littlewood and Hardy recognized, oh, we can construct a proof for this. We never knew this was a consequence. And they tried to explain to Ramanujan, you really need to, come up with, the proofs as well. We can do this for some of the ones that you sent. And Ramanujan, struggled with it and tried to do that. And he said, but it's not really my creation. It's Vishnu gives me these, and I just write them down. And so mathematics, the top dogs in mathematics, where are these ideas coming from? And for many, it's inevitable that they would have unavoidably a kind of a spiritual pondering as well. I mean, how is it? What do any of the number names name? Yeah, and I know I've shown you this before, but take a look at my two fingers. Two fingers have properties. They're whiteness and nailness, wrinkledness. They have some hairiness. Those are all properties of my fingers. Two is not a property of my fingers. Now, we use the name of two to describe our joining of two with perhaps another two and say, here we got four. But two is not the name of a property of my fingers. The only place you find two-ness is in the C-ness. I'm sorry, I couldn't resist that opportunity. But two is not a property of fingers. Two isn't a property of anything that exists in the world. And yet there's all sorts of properties of two. Two is two ones put together. Well, what do ones name? One. They don't name anything in the world. What does four name? It doesn't name anything in the world. But we use numbers to describe all sorts of activity in the world. And we're quite convinced we can reach certain conclusions, given the rules of mathematics, conclusions about mathematics itself, not necessarily outside in the world. Sometimes they apply, but nevertheless, we know whether or not we've reached a certain conclusion within mathematics itself. And we also know when we have reached a conclusion in mathematics that is uncertain or even wrong. Wrong in a sense that scientists can never reach. It's an absolute wrongness in mathematics. So it's a very alluring, mysterious discipline. And when kids first learn about it in arithmetic back in their grade schools, how come some of them go on to become accountants? They might be pretty good at that. Some of them go on to become a Ramanujan. Some of them go on to become a G.H. Hardy. Some of them to go on, probably the most famous woman mathematician ever was Emmy Noether. go on to become an Emmy Noether. Um, what did those people find in mathematics that led them to commit their lives to it? Why would Apollodorus wander the world visiting different mathematicians to do mathematics? Why not just settle down at a fine university and get researchers to work for you that you've taught and do the sort of thing that professors often do? But Ernest's love of mathematics just led him to chase mathematics. Perelman's love of mathematics led him to turn down great wealth, thinking he was undeserving of what mathematics had offered him. So it's really kind of interesting. So different from other disciplines. Whatever it is that brings people to want to study fictional literature, it's different than what we do in mathematics. Whatever brings people to want to study biochemistry, it's different than if you're going to study pure mathematics. And mathematics is obviously involved in chemistry and biology and so on. But those are applications of some of the tools of mathematics. They're not the study of pure mathematics itself.
Very interesting. Very, very deep. I'm not sure if you're aware, there is actually a movie that came out recently, well, a couple of years ago. It's The Man Who Knew Infinity.
Right, about Ramanujan.
Yes,
And it was
yes.
based on a book uh, uh, titled "The Man Who Knew Infinity."
Yeah.
He,
Very.
his interest was in number theory, and
So,
that's like Catholics are talking about saints, or you know, it's very ethereal. It's almost letting your imagination walk beyond the stuff that we encounter and think about these things out there in a celestial world made up solely of symbols.
yeah. So, I mean, this is deep and it can go on and on, but do all academic disciplines have a personality, like the way you explain
So,
the math personality?
yeah, I think so. You know, you get a chance to meet, somebody who is really committed to poetry. They might write poetry themselves, and they they see things that you just don't notice. Um, Go to an art museum sometime with somebody who is really an expert in art. And I don't mean an expert in art in a sort of way that they can talk about art history and tell you a lot of details, but they have actually studied in various ways what they think makes up art. And they've watched the evolution of art, not so that they can just tell about that evolution, because it's not an evolution that you can track into the future in any sense, but it's an evolution that draws you to very interesting details about art that otherwise you may not have noticed when you went to an art museum. All of us, when we were kids in any kind of large city, somewhere along the line, some teacher decides it's a good idea to take us to the city's art museum and walk around and show us stuff. And I remember as a child myself, I wanted to see the battle scenes. They were kind of nifty, but I wasn't looking at brushstrokes. I wasn't looking at composition. I wasn't looking at capabilities of showing depth. And wanted to go to the souvenir shop and wanted to get lunch. And that's the way most of the students that were with me, and whatever it might have been, fifth grade or something, that was our interest. However, many years later, had the opportunity to go to some big art museums with some people that really knew art, and they would point out things to me that I had never even imagined and would pass right by. I found that interesting, but not so interesting. I would want to become a student of art. I'm interested in anything I don't know. I didn't know that stuff. But even after finding it and going, that's amazing. I didn't know about that. I didn't want to spend more of my life looking for that stuff. That just didn't measure up to me. We all hope that our doctors know interesting things about biochemistry so they can treat many of the health distractions that slow us up from time to time. But we don't want to become doctors, and we don't want to become PhDs in organic chemistry to help out with the medical community. We're really interested in how well they do, but the nature of those sorts of studies just don't resonate with us. They don't ring a bell. And I think it's the same thing with mathematics. When you get to the upper levels of mathematics, you're no longer an engineer. You're no longer an accountant. You're up there in the clouds. And does Vishnu study or does Vishnu visit in the middle of the night and give you a theorem that no one could have reached without some kind of spiritual access? I don't know.
It reminds me of my own story. I struggled as a first-time college student taking college algebra. I struggled until I came across the ratio, golden ratio, right? When that came to me, and I was hooked on it, and then math became something that I wanted to learn, wanted to know, um, calculus and beyond, right? But I just would not even look at math when I didn't understand what the golden ratio is. But that's the topic that caught my attention. And then I started looking at, oh, okay, this picture, could it be possible? Is the golden ratio in there? Oh, this flower, is the golden ratio there? Is it true? Does it work? Going even into the spirituality, Sri Yantra, golden ratio. And it's like everything is connecting. It is really interesting once you find that hook.
Right. There's an interesting TV show that's just coming to an end at about this time as we're talking, and it's called Sheldon, Young Sheldon.
Yes,
And
yes.
there is one episode where young Sheldon tells well, first of all, he's trying to help a kid who is a slow learner with his arithmetic. And the kid that he's helping, uh, after they subtract something or whatever, and they get to zero, the kid goes, "So what's zero? That's nothing." And Sheldon's upset over that, and he says, "Well, no, zero isn't nothing, it's zero." And the kid says, "Yeah, but there's nothing there." And Sheldon gets distressed by this. And the more he thinks about it, he becomes increasingly distressed. And so he goes to two professors of physics at the college that he attends, even though he's like a 12-year-old kid or whatever. And he tells them, "I'm distressed because I've just figured out that zero doesn't exist." And they both scoff at that. Of course, zero exists. And the more he talks and the more they talk, they all become distressed. What if zero doesn't exist? Does that collapse all of number theory? Because we have all the positive numbers on one side, negative numbers on the other side. The number line is divided by a single number, zero.
Yeah.
And what is that? You can add 2 plus 2 and you get a new number called 4. You add 2 plus 0 and you're same place you started. You multiply 2 by 2 and you get 4. You multiply 2 by 0, you get nothing. Well, no, there is no nothing. You get 0. And it makes your head spin. The pure mathematicians love spinning heads because in the turmoil of all that, who knows what might come out of that? Another story of a great mathematician, the most extraordinary of all times. Um, well, we could even go back to the ancient Greeks, but Georg Cantor in the 19th century was a mathematician. He was interested in studying infinity. And Georg Cantor came up with the idea of the continuum. He also came up with the idea of the set of odd natural numbers has as many members as the set of natural numbers. 1, 2, 3, 4, 5, 6, 7 on infinitely. You can always add 1 to it, right? Set of odd natural numbers, you can always add 2 to it infinitely. And he reasons that each set contains the same number of members. Well, how do you know that? Because it seems like the one's twice the size as the other. But he points out odd natural numbers, natural numbers. You take a 1 here and you can draw a line to 1 down on the natural numbers. Go up to odd natural numbers to the 3, which is the next one that comes to mind. You can draw a line to it, to the 2. on natural numbers. You can go up to the next odd natural number, 5, and you can draw a line to it, to 3 on a natural number line. In fact, for every number on the odd natural number line, there is a number you can draw a line to on a natural number line. How long can you do that? Infinitely long, because they're both infinite sets. So they contain the same number of members. Oh my gosh, you're giving me a headache. And so Cantor would, people had been bothered by this problem for a long time. And Cantor recognized that when you talk about sets, you can skirt some of these problems. For example, since the set of natural numbers envelops the set of odd natural numbers, we can say that the set of natural numbers is bigger than the set of odd natural numbers as a set, even though they have the same number of members. That stuff is breathtaking. No accountant has to think about that kind of stuff when they're doing their job of accounting. So, people that are mystified by that stuff. And the interesting thing with Cantor, how difficult is it to really become mystified by this stuff? Fortunately for Cantor's family, he had a fair amount of family wealth. Because as he thought about all this stuff, it did drive him crazy, literally. And they would have to put him in a mental hospital for a while for him to calm down. And after he was more settled, they'd let him go again, and he'd go right back to math and thinking about the grandiosity of number theory.
Wow. This is very interesting, very interesting. Um, what do you mean by suggesting math as a personality? We covered this in the last recording, but if you could go a little more in depth.
More in depth on what now?
What do you mean by suggesting math has a personality?
I think for you to do pure math, you have to have an appreciation, interestingly enough, for ambiguity. I mean, people would say, "No, that's crazy. Math is just always, very precise. 2 + 2 = 4. Story over." No, it's not. For many applied mathematicians, one of the things that you want to do is find patterns where nobody else would notice a pattern. And so they're looking for patterns. They're looking for what tools math might give them to find a pattern that nobody else can suspect. And this isn't using the tools of mathematics to structure our thinking about the world we experience with our senses. Wow, that's really interesting that it can have that kind of power. How can it have such power to pull open the draperies that surround the interrelationships of material in the real world? And it doesn't stop there, because as we've already suggested with pure mathematics, it's almost as though one is also opening up the curtains to the possibility of spiritual events. Um, in the 15th century, there was a woman professor, first professor of female professor of mathematics at any university ever, and her name was Maria Agassi. And the Pope allowed her to be, she was a nun, and the Pope allowed her to be a professor at one of the universities, I think in Padua, but I'm not sure about that. And but she was a nun professor of mathematics. Does that sound extraordinary? Well, yeah, I think I've already given you enough to anticipate that thinking about mathematics seems to draw you into an otherworldly sort of mind, from the ghost whisperers up in Moscow to Ramanujan in India. And so this Catholic nun, um, uh, it's not surprising that a religious person fascinated by speculations into beyond what we can sense with our eyes, our hands, our nose, would find such intrigue in mathematics. So the
Think
the similarity between mathematics, pure mathematics, and the loftiest levels of theology should never go unnoticed. We can go way back to Plato, and Plato thought that there were forms, true forms, out there in some heavenly world, and part of that was geometric forms. You and I, according to Plato, we've never seen a real circle. We've never seen a real square. We've never seen a real triangle. We've seen instances of the real, but real triangles have 180 degrees within them, right? Real triangles. We'll come back to that in a minute. Anyhow, but they have 180 degrees in them. But Plato would say the triangles, the circles, the squares of the heavens are perfect. And any circle or square or triangle that we've actually seen hasn't got that perfection. It only participates in mirroring what's out there. In a dialogue he writes, Emilius, he asks a slave boy some questions, and out of the result of asking the slave boy a series of questions, the slave boy comes up with a solution to a geometric problem. And Plato has Socrates as a character in the Platonic dialogue. He has Socrates saying to those that were circled around him, see what the slave boy could do without any instruction. He was just recalling how things were in the heavens, because Plato thought we all started off in the heavens and then came here, but we have a mind that helps us recollect these perfections of the heavens. And so once again, you find this spiritual kind of element in Plato as he's talking about numbers and geometry. And by the way, think of how long when you went to school, when I went to school, they taught us some things about triangles, right? Right angle triangles. They taught us about the Pythagorean theorem, and they taught us lots of things about geometric figures, and we still use geometric figures as we imagine different dimensions. When we start imagining different dimensions, we get peculiar things happening. We imagine different dimensions that we've never seen in the physical world. But if these dimensions exist, there can be rules that reveal their structure. Let's take a structure that we can't imagine. Minkowski, Lobachevsky, a couple of, even Gauss, mathematicians that before Einstein had started contemplating that what Euclid had given us were straightforward, plain geometric rules. That is to say, a geometry of a plane, like what you see on a blackboard, what you see on a sheet of paper. But if geometry is to really reflect the kinds of things that exist, maybe we need to have a geometry that does not treat one of Euclid's axioms as an axiom, but shows that it can be proved. And if we do that, we might discover weird things about the world, and they do. One of the things that I did to teach a group of gifted kids one day who had already had high school geometry, so they all knew that all triangles had 180 degrees. And I took a basketball that I cut in half. And so I had one of the kids come up to the front, and he had a ruler. And I said, draw a triangle on top of this half of a basketball. And so he does. And of course, even with the ruler, when you look at the triangle he drew, it's bulging out at all three lines, right? Because the basketball's curved. So what if space is curved? Then one of the things we would know is that all triangles have greater than 180 degrees.
Yeah.
There are no triangles in curved space that are made up of 180 degrees. This was a necessary insight for Einstein to do what Einstein did with the special theory of relativity, and then later with the general relativity. And then I had these kids turn over the half a basketball, take a straight edge. Now draw me a triangle on the inside. And so they would draw a triangle on the inside. And what would happen when you looked at it? Everything is convex, right? So all the three sides of the triangle curve inward. And that also tells you about curved space. And so to Einstein and physicists that came after him, space is curved. You can't find, the claim of Einstein and others, you can't find a straight line anywhere in space. It's always curved. It's always a geodesic. Now we use that for practical purposes, like if you fly from here to say London, the planes don't just go straight line over to London. They go north and come down because we live on a ball, and the geodesic from New York to London is a shorter trip than if you went around straight toward it. Said there's London over there. If you go that way, you've got to go all the way around to get there. If you smaller part of our globe, you'll get there faster, less fuel used, and so on. But that curvature of space opened up everything that relativity had to offer us and what has come beyond that.
So this next question you sort of already tackled, but would still like your insights. What are some features of the personality of mathematics?
What are some of the features of the ideal person that in mathematics? Okay, well, let me kind of break that up. There are some people that are just good at mathematics. They went good at flashcard exercises. 4 + 6, 10, and so they were good at simple arithmetic.
Would you say somebody like Shakuntala Devi, the human computer?
Yeah.
Would she fall under that category as a personality of math?
Well, I would call that being very good at mathematics. There's one guy that befuddles me, and I'll tell you about him in just a minute. You can be very good at mathematics, meaning you calculate in your head very quickly. And it's kind of like athletics. Somebody can run faster than somebody else. And you take pride in that excellence. And so somebody who can calculate very well, whether it's with division or addition or multiplication or whatever, that's something to be proud of. But the heroes of mathematics, well, let's say that with very good. Very good. Think of people who do well in engineering. Think of people who do well in physics. Think of people who do well in those kinds of lofty mathematical areas, but they can't quite have reached the areas of a Grigori Perelman or David Hilbert or a George Cantor or Paul Erdos and so on. Those people are just extraordinary. They're the angels of the mathematical heaven. A guy that comes to mind when you mention calculator, there's an incredibly famous guy responsible for building the first computer in this country. He was also one of the people who at Los Alamos to advise on the making of the atom bomb and the chances that once we split an atom, well, we only split the atoms we want to split and not just cause a never-ending split of all atoms in the universe. His name was Johnny von Neumann. And von Neumann was a character. He loved to party. He loved to drive recklessly. Nobody wanted to ride with him because he was a horrible driver. And but everyone recognized what a genius he was. In fact, the first woman who ever designed programming languages was not somebody called Lady Ada. It was von Neumann's wife. He's going to marry somebody that has, that shares that same kind of interest with him. And he was part of the design of the first operating computer in this country. And his wife, he had her design the instructions for it after they were talking about it and so on, and she did. But Johnny von Neumann was famous for, first of all, being around big guns in physics and math and they would give him mathematical problems, and he would solve them like that. Then after we started developing calculating machines that were really fast, they would give he and the computer the same mathematical problems to see who could solve it faster. Von Neumann himself with his computer, or the machine, which were, big machines for calculating, even then. I mean, the early days of the computer, its ace in the hole was unbelievable skills in calculation. And we had calculators even before we had our first computers. So, yeah, calculation is one type of thing, but von Neumann is one of those characters who wasn't just very good at math, so he could calculate better than our computers, but he also was a pure mathematician as well. He thought about the possibilities of math. He thought about how you could use a binary operation in a mechanical machine to mimic human thinking in well-constructed frameworks. Wow.
So artificial intelligence is not new.
I'm sorry?
Artificial intelligence is not new.
Oh, no, it's been around for a long time. Let me show you something. I got a book to show you. This is Princeton University Press. And what they did, the book is called Do Not Erase. What they did is the authors went around the top mathematicians in the world, said, can we take photographs of your offices? And they said, yeah. So the layperson still tends to think that computers are the heart of the mathematical enterprise. No, they're not. And the top mathematicians aren't going to the computer necessarily to solve all the problems. They use them at times, and they're certainly good at it, designing things too. But here's what a mathematician's office looks like. There is a chalkboard. Chalkboards are almost ubiquitous still in real mathematicians, pure mathematicians' offices. And I'm not even looking at what page I'm opening for you. I'm just doing this at random. So you just see the blackboards and the offices of two different mathematicians. I don't even know who they were, but they're all something like that. Here's another one.
Yeah.
I could just keep on doing this all day, but this is what pure mathematicians are still all about.
Yeah, we're definitely gonna list that, leave a link in the description so the whoever is interested can check that out. But that's pretty interesting because you would think with the way technology is skyrocketing, people would more depend on AI. Everybody's talking about AI, but it's all in there.
Well, it's curious, one of the things that you hear people talking about right now is quantum AI, and um, they're very ambitious in what they say quantum AI may choose or may do for us. But one of the problems with a qubit quantum AI, we know that any particle in an atom can jump quantum leap. You've heard of quantum leap. Uh,
Yes.
a quantum leap doesn't leave a trail. What we mean by the term quantum leap is the particle, or maybe a packet of energy, seems to jump from one orbit to another orbit on the inside of an atom without going anywhere in between. Holy smokes, how does that happen? And so we have something called Feynman diagrams by the physicist Richard Feynman. And what Feynman diagrams do is they give us a probability of paths that the quanta might take. And we don't know which path it'll take, but if he's right, we can identify with a certain distribution of probabilities which path it's most likely to take. But we can't track it going from one to the other. And so even with quantum computing, it's not clear that it will do what our wetware, that's the key, the in word for our neurology, what our wetware does when we make a judgment, whether it be a snap judgment or a reflective judgment that seems inspired. You've got a lot of biochemistry to talk about in this wetware. can the quantum computer ever capture what's going on in the wetware? For it to do so, we would have to be able to map out all that goes on in the wetware down to the molecules. Molecules are made up of what? Atoms. Atoms are made up of what? Subatomic particles that we call quanta. Well, if there's subatomic particles inside there, you've also got quantum leaps going on. And so Feynman diagrams only give us, probabilities. They don't tell us the kind of track that would say AI aligns in an isomorphic fashion. That means one-to-one with what goes on in the brain. Can it match it close enough to be useful to us? Well, sure. I think that'll occur. It'll be useful to us, but we have to make sure that we don't trip over ourselves and superimpose it on areas of reflection that it doesn't fit well and yet may be very, very important to us. Have, uh, this will be a little aside, but just to illustrate that, have you heard of Sophie's Choice? It's a moral film. Sophie's Choice. The Nazi officer tells Sophie she has a boy and a girl. This is back during the Holocaust. Says, "Do you want us to? I'm gonna kill one of your kids. If you don't choose which one I kill, I'm gonna kill both of them, and you got to make a decision right now." Now, that's a difficult moral question. Can AI answer it? We don't even know what the answer is, do we? But Sophie answered. And we do answer problematic moral issues. We have to do it all the time just to survive. And we're not always sure that we got it just right. Sophie wasn't sure. But actually, the original Sophie, there was a movie made about Sophie's Choice, and there was a book written about it. But the author actually met a woman who was not called Sophie, but told him that story, and she had to face that. And is there any way that even with a quantum computer that we can do a better job of answering those sorts of things? I can't even imagine such a thing. But that's one of the beauty of mathematics, right? It is. It's it's like discovering when you go into the art museum with an art specialist. Oh my gosh, there's so much more going on in here than I ever realized before.
What was the name of the movie once again? Whose
Sophie's
Choice?
Choice.
Sophie's Choice. That's the name of the movie.
Yeah.
Sounds very interesting. Um, so moving along with our questions, you talk about categories of people who learn to do math to varying degrees. For example, you talk about those merely competent in math. How are they identified?
Well, I think like we identify. Well, let's say I'm going to talk about three ranges of people. People who are good at math, people who are very good at math, and the heroes. And the people who are good at math become competent CPAs. People who are good at math become competent engineers. Um, People who are good at math can run the equations, can utilize the computer to get results that they understand as appropriate to the situation they're trying to figure out using math. Those are people who are good at math. Um, if you wanted to reduce it to a grade school situation, there are the people that tend to win. If you have a contest, half the class is over here and half the class is over there, and the teacher has flashcards. How much is 6 times 6 or whatever. And the kid that answers first, okay, go to the back of the line. This is the team that's winning. That kind of stuff looks like you can, and I think it does identify people who are, good at math, very good at math. Now you're looking at the kids who can take trigonometry at their junior or senior year of high school. They can do a pretty good job of understanding the reason for linear and nonlinear calculus. And they can go on to college and study engineering. They can go on to college and study the mathematics of probability as it's applied to different statistical challenges in the sciences. Um, those would be people that are very good in math. If you have a financial advisor, financial advisors are very good at math. But then above very good at mathematics are the people who have gone well beyond them and have, in a sense, find themselves enslaving their mind to solving mathematical problems. There are people who aren't as excited about getting an answer as the people who are good or very good at mathematics are excited. That's what they want to find. The people who are the heroes of mathematics are looking for problems that they can't solve. And then they'll try to solve them, of course, but they'll spend all sorts of time on it. Probably the most famous one that I can think of offhand is Fermat's last theorem. Fermat was a mathematician back in the 18th century, got in a sword fight the next day. The day before, he came up with what he thought was a proof of something, and he wrote in the side of his work, that he has the proof for this. Well, the next day he goes out and gets in a sword fight over a lady, and he didn't do so well at sword fighting as he did in math, and so he lost the sword fight and died. Well, we have this proof missing. We have the claim of the great mathematician that he has a proof for this theorem, but no one could ever find it. So mathematicians, the heroes of mathematics, spent years and years to try to find the solution. How many years? Approximately 350 years before the proof that Fermat said he had became available. It also involved the details of computers to get us through just parts of the proof. And a mathematician from Princeton in the 1990s was a fellow that solved it. His last name was Weil, Weil. Other mathematicians over time had made small advances toward a proof, but no one could get there. 350 years. There were mathematicians who lived and died, who spent much of their life trying to solve that one problem. Yet after a lifetime, they still hadn't solved this one problem. 350 years. And Fermat's last theorem was extraordinarily famous for its, come on, mathematicians, see if you can solve things. And the heroes of mathematics, ran to the race to try. And it took them 350 years. Lives have been spent, and not worthlessly. A hero of mathematics wouldn't see that as being worthless effort. Of course, the grand prize is to solve it. And before Weil came up with his solution, there was a guy over in Japan that had done a lot of work utilizing computers to help advance our cause that Weil depended upon. And then mathematicians do what they love to do best. Here Will comes up with his solution, and mathematicians all over the world immediately went to try to falsify it. I mean, how did you come up with a solution when 350 years of mathematicians trying to solve it weren't able to do it? And no matter how much mathematicians looked and looked and looked, they couldn't find even a tiny little error in his proof. And it was, he did it. Now, pure mathematics is almost like a sport. Your financial advisor who may be good at mathematics, or an economist may be very good at mathematics, and directs our attention to different economic policies we ought to employ and so on. But they may not be that good. Sometimes there's a guy named Kenneth Arrow who got the Nobel Prize in economics, and for what? Arrow, it was called Arrow's theorem, and it was about he thought he had proved mathematically the impossibility of mathematics capturing the will of the people in any voting system. Arrow's theorem.
Wow. So how how are you mentioned it, like there are good um, people good in math and very good at math, right? How are the people who are good in math identified?
Well, I think those are identified with standardized testing. Math lends itself very easily if you're looking for who's good at math. Standardized testing works for that. Solve for X, and so we can identify people who are quick at that. Idiot savants can be really good at that, but that doesn't mean that an idiot savant is going to be good at contemplating um, the heavenly excursions to the edges of math. But they're really good at calculating. I remember there was a pair of twins. I'm sorry, there was a set of twins, and nobody could understand this, but it's one of the things you find sometimes with idiots savants. You could take a box of matches, like kitchen matches, open it up, turn it over, just go plop, and the two of them would just look at it and look at each other, and then tell you how many matches were there, and you'd count them up, and they were right. How did they do that? Because remember, they're idiot savants. So they're having all sorts of trouble with other sorts of thinking practices. But boom, they get that. It got even more mysterious. If you took one of the twins and put them in another room, and then you take the matchbox and you open it up for each of them, you open it up and boom, what do you see? They couldn't come up with an answer. You put them together, and in an instant, they look at it and they look at each other without talking. And then they come up with an answer. How do you explain? I have no idea. But they don't count as mathematical heroes, but they certainly do count as somebody who's very good at certain calculation skills. Like in this case, adding them up. I don't know how practical that is, but what it does do is give us evidence of somebody who could. If you gave them a standardized test and you had the two of them sitting together, and you'd say, well, these kids are just great at basic mathematical maneuvers. So standardized testing, solve for X, can pick out the kids who are good. Uh, and to get to be very good, you've got to be good at least, right? That's on a track. So we can pick out the kids who deserve to get through college. We can pick out the kids who can get degrees in engineering, can get degrees in bachelor's degree in physics, um, accountants, statistics. But now, if you want to go beyond that uh, to the very good, well, the race gets a lot tighter. And to get to the heroes of mathematics, then you're looking for Olympians.
And those who are not really focused on the fame.
Yeah, yeah.
Very, very interesting. Very interesting. As always, I learned so much more each conversation. I learned a lot. And what I said in your classroom, I'm going to tell you again. You make my brain hurt in a good way. You always take me to another level, and it helps me grow. It helps me grow because it forces me to think, really, is this how it works, or could it be this way? Like I'm questioning my own understanding. So I enjoy these conversations. One really out of the box thing here, there you always have a company. Almost every video we have recorded, you have your little friend in the background, and someone has brought this up. So I'm gonna ask you, why do you have the angel of death? Like in my culture, it's the Yamraj or Yamdut, your grim Ripper. Why do you have him? Yes, why do you have him? Like you're always celebrating Halloween or something?
Well, in a sense, death is part of human existence. So we all know that all traditions and cultures have symbols of death approaching and of death happening. Uh, no, I'm not morose in having him there, but in a sense, he's symbolic of what happens if you let your intellect die. You can live another 30 or 40 years, but if you let your intellect die, why? But what are those 30 or 40 years made up of? So in a sense, that's not a symbol of moroseness, but it's really a symbol, a reminder to keep your mental life alive, because that's probably the most important part of you that will enjoy living.
Wow. But death, I mean,
Well,
that's very interesting.
yeah, yeah.
So, Dr. Wagner, once again, thank you so much for spending giving us this opportunity to discuss and learn more about the fascinating world of math. We do have many more questions. Well, we'll have to do another video, part two, part three, maybe part four. I'm not sure. But these interesting conversations should go on, and I know that a lot of people do enjoy this. This is not a traditional podcast, but I know that people who want to learn, who are interested in this type of applications in almost everything we do in life, because math is not just numbers. Just from the conversation today, it can be spiritual, it can be uh, in the field of math itself, it could be in biology, in biochemistry, in chemistry, whatever you want to call it, even in business, in accounting, it can all work together. um, just that golden ratio thing, I mean, that still boggles my mind, like how does that work? So it is really amazing to have someone with your knowledge and your expertise explain this and dumb it down for people like us, who can actually make sense of it. So thank you so much for this conversation and many more to come. Uh,
Namaste.
namaste. With more details on this book and other works that you have already done or what you're working on, we're gonna leave links to the description box, so people that are actually interested in reading the book or obtaining their own copy, they can go to Amazon or wherever it's available. And also, I'm going to request people that are actually enjoying this kind of content, please share and subscribe to this channel, and share with other people so we can keep people thinking, and your little death friend right there can keep reminding us, don't let your intellect die. Keep your mental health always on the go,
Yeah.
just as as people think about their physical health being important, mental health is also as important, maybe more, because if no brain, nothing matters.
It's the great conversation of humankind. Everyone's invited if they'll take the time to join. And everyone is welcome, but they have to recognize that it's a matter of rolling up your sleeves and thinking and asking questions and not being embarrassed by any question one might ask. Or else, if you don't, that's who's looking for your mind.
Yeah, yeah. No, thank you once again. Um, we'll definitely continue this conversation on personality of math. And if anyone who's listening or would like us to explore other topics after you read about the works of Dr. Wagner, please do reach out to us and let us know. We'll try our best to bring those sessions in the future, and that way Dr. Wagner can share all that's in there in his mind and in his brain, because we all deserve that. And thank you for sharing that knowledge. Thank you for sharing the wisdom you have. All right, Dr. Wagner, we're going to end our session here. Once again, thank you. We'll see you next time. Bye bye, sir.